the ionization event, you end up with a large piece of the wave function sitting in a very localized region of space, and a small piece of it that travels very far away, tens and maybe 100 atomic units, right? And is picking up, having its phase greatly modified by the field in a way that the other piece is not having it modified. And then you bring these two things back together, and you look at the interference that you get, right, the time-dependent dipole, and the phase beating between these two pieces. So it's quite spectacular.
Because of these interferences, you could also say it's a bit like a braking action.
Right. I wouldn't dispute that. I think that's fine too. And then it doesn't get a certain number of people that have very specific ideas of what Schrodinger cats are upset, because it's not the point. Right? I mean, you often find this in physics, right? You use a certain language and then a whole bunch of people get upset, and then you say, well, I didn't even, it wasn't even important that I said that. Could we get back to what we were talking about, right?
But you can't publish a PRL with the Schrodinger cat.
No, that's true. So here is an example. Here's the release time. Here's a half a cycle of the laser field. And the laser would have peaked back here at the quarter cycle. And now, as a function of when you would release the electron, and this is, again, kind of a classical calculation, here is the return energy that you have, because that determines the frequency component of the polarization that you get. And you can see that for most return energies up to this cutoff, which is a little bit above 3 UP, there's at least two ways to be made. And when you go below about 2.4 UP here, you have even more ways. So first you have 2 ways, then you have 4 ways, and you have 6 ways. So it brings in successively more and more ways that any given harmonic could be made. So the maximum energy is given by the ionization potential. That's the binding of the ground state. And the 3 UP is what the continuum piece could pick up. And then it says, like it says there. If you're sort of thinking about why it is this classical description for the piece that goes out into the continuum work, I guess I would say for that, for one thing, the density of states there is really high, right, in the continuum. And so you should always be able to get back to a classical description, more or less, in such a case. Yes?
So I'm a bit confused about the spatial profile of the emitted radiation. So if the light comes along the z direction and the dipole oscillates along z, and right?
No, the light is traveling along z, so it's the polarization is oscillating in the perpendicular direction. And so then the polarization is in that direction, and the emission will be again in the direction of the propagating light.
So it will be, yeah, okay, but also sideways.
Yeah, all the sideways. It has cylindrical symmetry.
And, yes, and what happens with the sideways emission?
No, there's no sideways emission. Well, actually, I have a good slide on that too. So if you'll let me get to that slide, I'll show you that. Wonderful question. So the other thing I want to say is when you think about these space-time trajectories and you say that you could calculate them classically, the sort of way to put that on a firm quantum mechanical footing would be to say that, well, I have a bunch of possible space-time trajectories that I can take. And what Feynman would tell me to do is calculate all of them. Calculate the classical action for each of them. The classical action here is dominated by the field. That's the energy that the field is giving. And then look for who gives stable contributions to that action. In other words, I have the dipole moment contributing to the qth harmonic. I have a whole bunch of different space-time paths that could give rise to that, corresponding to ionization time, t prime, and a return time t. I calculate the amplitude for each of those. I tack onto it, e to the I, this phase. The phase just comes from the classical action. And then I ask myself, who makes the biggest contribution to this sum, right? Well, it's going to be those paths for which the action is stationary, for which it varies very little. And when you have a very high density of states, when you have essentially a situation where classical trajectories are allowed, those will also be the ones that have actions where small variations are stable. And so this is my one slide sort of try to get you to think that maybe it's okay to think about these classical trajectories. They are the ones that make stable contributions to this sum over all possible paths. Think of all the paths that you want, but just do as Feynman said, tack onto each one a phase, which it gets from basically the kinetic energy, and that kinetic energy comes from being accelerated in the field. So this is why we can do this. It says only a few paths are important. We often say that it's only the first two. It's actually more like the first 3 or 4 in most cases, unless you really look at the high frequency radiation. Okay, so let me think about, yes?
I am a bit confused.
What is my time?
You have
When am I aiming for? What's,
another 20, 25 minutes.
okay.
So the final state for this electron, which is making harmonics, is the ground state, right?
So this is not my view of it. I mean, in other words, if we're sticking with that the electromagnetic field is, in other words, it's not the most consistent view. It's fine to say that the final state is the ground state, yes. But let me give you another way to think about it, which is that since we're thinking about the electromagnetic field classically, right? And what we care about is what is the polarization response of the atom, right? And the polarization is big when you have two states, that you get a high frequency polarization that's big when you have two states that are separated far in energy, that are both occupied, and that have a high spatial overlap. And that's what happens as this wave packet comes back by. So there's no need, in our calculations, nobody makes a transition back to the ground state, right? Because there's no way to release this energy to the field. It's a classical field. So it would be much better, I mean, I understand recombination as a very easy to grab onto concept, but it's not instantiated in the calculations because it would be treating millions of photons with a formalism that was most appropriate for one photon per wavelength, per cubic wavelength. So here's the recipe. Let me just say this. So the recipes that people employ, and then I want to say why phase matching and macroscopic effects are important. You would say, I've got a gas of atoms, here they are, I put in frequency omega, this is the driving frequency, and I get out of it a bunch of harmonics. And I get this nice plateau, and then it has a cutoff somewhere, which we had to convince PRL was one word. They didn't want that. And so here's the first sort of selecting, right? There's no attosecond pulses here. This is a single atom spectrum, there's no attosecond pulse. So you start doing selecting, filtering, gating, to try and get to attoseconds. One thing you can do is spectral selection. You can choose some of these harmonics, right? You have a comb of harmonics in the frequency domain. That leads to a train of pulses in the time domain. The bandwidth of each, the time of each of these pulses is inversely proportional to how many harmonics you select here, right? And the time envelope of the total train is given by the inverse of the frequency bandwidth of one of the harmonics. Okay? So the bandwidth of one of the harmonics determines the overall time structure. The bandwidth of all the harmonics together determines the time structure of the individual pulses. So a lot of harmonics give you very narrow individual pulses. Another way to do this would be to say, I'm going to spectrally select only the harmonics right out at the highest energy, and I will say that there was only one way, that one time that those could have been made, and I would get maybe a single pulse that's maybe 250 attoseconds long. And this is the recipe that was implied. So for instance, if you think of this as sort of a spectral selection, right? Here is in time, here is the energy of the returning electron, and you can see for most energies, there are 2 times when you can return. But as you get out to the highest energy, the cutoff energy, it really gets squeezed into basically only one way to make it. So again, we can think of spectral filtering where we did have 2 pulses, right? If we were talking about energies down here. If we select energies only out near the cutoff, maybe we can get only 1 pulse somewhere else. And so this is an example of spectral filtering as a time gate. And it's this sort of back and forth, push me, pull you, sort of between time and space and frequency that actually gives you attosecond pulses. Another example of this would be if you have attosecond pulse trains, right? So here would be the pulses that you would get if you just thought about a single atom. So you get every half cycle, you have many different bursts of radiation because you have all these different trajectories that can give rise to things. But if you look out near the end of the plateau at 2.8, then you get down to just 2 bursts per half cycle, that's the red. And if you look right out at the cutoff, you have the green. And if you look back here in the plateau, then things get even more complicated. So you can filter spectrally and get a different time behavior. So now let's look at the standard recipe. This is what you would do to make single attosecond pulses. More or less today, this is what's following. You would take the shortest driving pulse you could get, say 2 cycles, 4 to 5 femtoseconds, maybe even a little less than 2 cycles. You'll do spectral selection, look only at the cutoff harmonics, and you will have carrier phase envelope control so that in your 2 cycles, maybe only 1 or so delays will be important. Here is the carrier envelope phase, so here's the envelope of your light pulse, your driving pulse. Here is the actual at a given. So as you change the carrier envelope phase, you see how the form of the electric field of the driving laser changes. For some phases, you get basically just 1 big pulse and 2 smaller ones. For other phases, you get 2 big pulses, right? So by changing the carrier envelope phase, you change how many ionization events are important. So this was the idea that Krauss and his group were following. They said, let's control the carrier envelope phase of a few cycle pulse. If I choose the carrier envelope phase correctly, and I select just out at the end of the plateau, I will get essentially 1 single attosecond pulse. And if I change the carrier envelope phase by pi/2, go from a cosine to a sine form, then I'll have 2 ionization events, I'll get 2 pulses. And they do this, and it really does kind of work. And now we come to it. But wait, aren't there many atoms, right? So what's really going on? Well, what are you measuring in one of these experiments? Certainly not the radiation from one atom, right? The radiation from one atom would go in a dipole pattern, which is very broad. And the radiation that you see coming out of the end of the medium is really narrow. It's milliradians. So it's very narrow, right? Because what are you measuring? You're measuring the electric field emerging at the end of the nonlinear medium, or really you're measuring the square, but you're measuring the intensity. And sometimes you can do experiments to measure the phase as well. But certainly that's what you're measuring. And so what you are seeing is constructive interference in the forward direction. So all the radiation that goes off to the side adds up incoherently, interferes to nothing, and you get a very strong, very narrowly focused, essentially laser-like, even though it's not a laser, right? You can point this at stuff, right? Which you can't do if you just had a bunch of dipole emitters and sort of randomly going. So you need constructive interference in the forward direction, and that is what's seen. So you have all these little dipoles working together to get the radiation going in the forward direction.
Now, why do they work together?
Well, truth be told, they don't work all that well
Right.
together.
Yeah.
But to the extent to which they do, this is what you see.
Okay.
I mean,
But
in other
do you
words,
have to
this
work
comes
to
back
get-
to the phase matching issue.
Right, so do you have to work hard to get phase matching, or is it kind of happens?
So it happens, and it's not great because the conversion efficiency would be something better than 10 to the minus 6 or 5 if it worked really well, right? I mean, in a BBO crystal and you're doing second harmonic generation, the efficiency is 50%, right? So it's way, way off that, right? It's because the coherence length is very short.
Right, okay.
All right. So you need a large medium to get a lot of signal, but the coherence length is short. So there's a trade-off there.
And you can't do the tricks that the older guys like Bloomberg and the quasi-phase matching and things like that.
Right, right. They essentially don't work.
Right.
What is the coherence length?
Here's the thing, and I think this is like an important lesson. There's two essential aspects to this. Number one is you really want the light. For many, many years, and maybe for many years to come, if you have just a normal laboratory and you want some XUV, short pulse XUV radiation, this is your way to make it, right? When somebody makes something that's 10% efficient, might be out of business, right? That's okay, because I'm not really in the business, right? I'm just a theorist. So the point is, you really want the light, right? The other is it runs on water.
It's what?
It runs on water. The fuel is water, right? The fuel is these IR photons, which are fantastically, incredibly cheap, right? So it's those two things that work together to beat the fact that the phase matching is not all that wonderful. Is that semi-clear? Yes?
So what is the phase coherence in this case? Sorry, coherence length. Sorry.
It varies. I mean, that is the thing that varies as you change everything. So it can, and medium length. You try and get something that's a fraction of the medium length. So I'll show you that in a minute. So what is phase matching? Just for, I think Paul said it well, but I'll say it with an equation. You have to match the phase front of the propagating XUV light to the phase front of the newly generated XUV light, right? So the XUV light made at the back of the gas, when it propagates to somewhere in the middle where new XUV light is being made, you would like that to be in phase. So they would go off together, amplifying each other, okay? And to some extent, they do that. So the Q harmonic wave vector is K sub Q. The length of it is just Q times omega over C, basically, omega being the driving. And what direction is it heading? Well, that's what you learn from phase matching, right? The direction of the source radiation is given by the derivative of the phase. So you have a spatial phase. The gradient of that gives you the direction of the source, right? So that you can think of the radiation as going downhill in some sense, right? So if you have flat wave fronts, then the radiation will just go in the perpendicular direction. If you have a curved wave front, then the radiation will be dispersing. And this is exactly the question that you're asking, I think, right? Which is, why is it sometimes broad? Why is it sometimes, where does it go? And so if you think about the wave equations that we solved for the harmonic fields, for instance, you have a transverse derivative, you have a longitudinal second derivative, you have the linear term, and you have the nonlinear polarization that's driving this, right? It's this nonlinear polarization that you need to calculate from some solution of the time-dependent Schrodinger equation. It could be a really good solution. It could be an approximate solution. It could be something you make up. But whatever it is, that's then what is going to be the source term for you in the new radiation. And so you get things like this. So first off, what is the focused laser beam doing? Well, the focused laser beam has wave fronts that are diverging outward on the back side of the focus and are going, inward on the back side of the focus and outward on the front side of the focus. So the laser light is traveling from left to right, and the wavefront is changing. It's being flat right in the focus, and so you have this this gooey phase shift of pi as you go through the focus. So those are the wavefronts that do the focusing. You also have a dipole phase, right, which is the phase of this dipole radiation, which turns out to be proportional to the intensity of the laser light. And the main message, which I don't want to belabor too much because it's a real detail, but you can ask me about it in as much detail as you want afterwards, is the different space-time trajectories that we've been talking about. These are characterized by alpha sub I, or coefficients, which for what we've called short trajectories, these coefficients are very small, and so the phase of the light is not very sensitive to the intensity at all. And for the longer trajectories, this phase is really big. It's like 10 times bigger. And so those trajectories give rise to light which is very sensitive, to phases that are very sensitive to the intensity. So now remember, phase matching means that you want to match the emitted wave vector somewhere in the gas to the emitted wave vector somewhere else. And this comes from the gradient of the phase due to focusing of the laser and the gradient of this dipole phase. And you have to make these things work together in order to get it. Right? And so essentially you get two kinds of phase fronts from the single atom solution. You get, for tau 1, these are the short trajectories, you get phase fronts that are slowly varying in R and Z, they're gently curved, so they give rise to light which goes just in the forward direction, very narrowly focused. The longer trajectory phase fronts have a strong intensity dependence to them, and remember, as we go off axis in the laser pulse, it's focused, so as we go off axis, the intensity drops, and so the phase varies, and so the phase front will be very curved, and you'll get things that diverge. So when you look at the single atom level, it's really, really hard to tell the difference between different trajectories because they're all mixed up together in there, right? The only thing you calculate is some amplitude for something to happen, and you get the amplitude for all the different ways that it happens. So all these trajectories are mixed up in your single atom solution. But in the far field of the propagated solution, they separate spatially. The short trajectories give rise to light that only goes forward, and the longer trajectories give rise to light which is more divergent. So in the far field, it's no trick to separate them as long as you have signal. The trick is to get signal. So different macroscopic phase matching for different microscopic quantum trajectories. Yes?
It's kind of a naive question, but can you get better conversion efficiency if you use like a thin solid film instead of a gas? Because then you get more atoms within the coherence length. I know that there are other processes that can spoil this, so I don't know.
So people have tried this for many years. They've tried different things. They've tried liquids. They've tried very thin solids. They've tried clusters. That was a really good idea. So now, and you'll hear it from in Paul's talk, people have succeeded in seeing harmonics from very thin materials, thin crystals. The main problem with that, as you would think, is you just destroy it, right? Because you're putting a lot of intensity in, and you're doing, 10,000, 1,000 and 10,000 pulses per second. I mean, it's just a damage issue, right? The gas is great; it just heals, right? Right away. But the material is not. But so now, in principle, people are seeing harmonics from solids, and maybe they can get the number up with phase matching and all that. At the moment, the actual number of photons coming out of the solids is very low. So it's not just turning it on, but there is something there. And the numbers of photons that people got out of clusters and liquids is also very interesting, the process by which they're made, but it doesn't beat just go get a very big laser with a long focus and a high gas density. And, that's what you're competing with. It's a little bit like the solar energy problem, right? It's really cool to make solar energy, but then you've also got to compare it with how you're getting the cost for how you're getting energy now, right? If you're really going to get people to switch over.
But not in Arizona.
Hmm?
But not in Arizona.
Not in Arizona, that's right. So the other thing, the last thing we need is, what about the laser beam itself? It's propagating through a rapidly ionizing medium. No ionization, no harmonics, no radiation, nothing to talk about, right? So there must be ionization in the medium, and this actually affects the driving laser because your ionization is producing free electrons that oscillate in the field, and that will produce a response which is proportional to the driving electric field and the number of electrons that you have. So here's the second derivative of the polarization. These freely oscillating electrons make a contribution to that at more or less the driving field, and they change the refractive index. So you get a negative contribution to the refractive index. Varies in space and time. You get a large negative contribution to the refractive index on axis, because that's where the intensity is high. You get a smaller contribution off axis. And so what happens, I think it's on the next one. I hope it is. Yeah, here we go. That the beam diverges. In other words, here is your driving laser beam at the beginning of the medium where there's no ionization, and as it goes through and it starts to make ionization, the phase front starts to get bent and it diverges. So ionization puts a real cap on the maximum intensity that you can get in the medium. All right? You really can't just blast it all to plasma. Okay? You won't get to that high of intensity. So it makes the laser beam diverge. More than that, though, it adds a time-dependent phase to the laser propagating laser field, which corresponds to a change in the laser frequency. The change in the laser frequency turns out to be proportional to the rate at which free electrons are being produced. And since dN dt, right, the number of free electrons that have been produced, it's always 0 or some number bigger than 0. So, and dN dt is always a positive number. So you always get a blue shift or even more a chirp. So as you have, let's say, here's time. If I have a small amount of ionization, I'll get a small blue shift on the laser field as it goes through the medium. If I have a lot of ionization, I'll get a large blue shift. And this actually changes the frequency of the driving laser field. So the frequency of the driving laser field, if I have a lot of ionization, it can be very different at the front end of the medium than from the back end where I enter it. Okay. We're almost ready for the good part of the story. So altogether, you got this intense pulse propagating through the ionizing medium. You got the spatial temporal shape changing dramatically. You got phase matching or not of the XUV radiation. And so you get these attosecond pulses. They're generated by a macroscopic number of things. So if we want to describe an experiment, we have to simultaneously solve the Schrodinger equation and Maxwell wave equation in what are pretty extreme conditions. We would, both for the Maxwell equation and the Schrodinger. Strongly driven, non-perturbative thing. It's a HPC level problem, strong field nonlinear optics. Here's again to remind you what we want to do. We want to solve the Schrodinger equation marching in time, with Maxwell equation marching in space. These are coupled by the polarization that is induced at any place in the medium. How do we get to this? Let me just say this in 2 slides. You start with the full Maxwell wave equation. Here it is. So here's the polarization that's driving it. Here's the electric field. You move through the gas at the speed of light. So you change to a time t prime, which is t minus z over c. You don't have to pick the speed of light. Pick the speed you want, all right? You could pick some group velocity or something. That would be okay. In the transform time, here's now the Maxwell wave equation. And because I picked to go with the speed of light, I actually get 2 terms here that cancel. It's okay. If I had picked the group velocity, I would just have 1 over c minus 1 over some group velocity. This second derivative in time term is no problem to handle. Okay. But the simplest form is to pick the speed of light because it kills this term exactly instead of leaving a small term. What is the term we dropped? We dropped the term that was the second derivative in z at the t prime coordinate compared to the term we kept, which is this one. It's this mixed